Okay, so let's move on and now talk about large model support. So I will go pretty fast there. So you know that models are becoming more non-complex. Images and videos are moving from high res to 4K. So so we need to process larger images as well as a bigger model architecture. From if you remember the classifier, and now we are moving to instance segmentation, which requires very big models. So oops, I'm going to switch to. So deep learning is the training is definitely memory constraints. So you know that GPUs have limited memory. So neural nets are growing deeper and wider, and the image resolution is also becoming bigger, and we have access to a lot more like images and data nowadays. So if you consider what is the maximum, what is the size one V100 GPU can handle? So ResNet, you know, if you take a ResNet 101 with the batch size 32 based on images 112 by 112 by 3 RGB channels, it's about 22 megabytes. So it's really not that big compared to the 32 gigabyte cache you have in with 100. So same for the classical 3D ResNet also training. So it's not a big pressure for the GPU memory itself. But there is some cases. In this case, medical images typically, where the images are very large. So chest radiography is are getting very big. If you consider 3D CT scans, it's 2 gigabytes for one single image. And there is also this, you know, this wide slide images, which takes hundreds of gigabytes. And where you can actually see all the different cells in the tissue. It's very, very large. So there is different approach to handle these very large images with very high resolution. Either, as you know, that you can't handle them at once in the GPU memory. You have first you can consider first to down sample them. Okay, so reduce the resolution, but for sure you will lose information, and you will there is all these tiny detailed objects that you are going to not detect typically. Or the other approach is to patch or tile your large images into sub images. In this case, and then apply the model on the different sub images, on different patches. Then in this case, there is other problems that could occur, like, you know, the scaling of objects that could be, so the detection of, I would say, same object class, which with different scaling. And also, once you have all your model as infer the different patches, you have to actually assemble the results, so and it could lead to a complex post-processing phase as well. And sometime another model could be involved to do the reconstruction. So to handle that, Watson machine learning computation introduced large model support to actually train these large images. So the idea is to roughly utilize the system memory of your AC922 and transfer or swap tensors from the graphical memory to the main memory. And that could be done thanks to this NVLink awesome performances. Because not only the NVLink is pretty fast in terms of bandwidth, it's also have a very low latency compared to PCI, especially. So it can allow you to train bigger models with bigger tensors between processed by the different layers, or directly work on native image resolutions. So without doing downsampling or patching and so on. Or if you are doing patching, use larger patch size. That's also another way to use it. All right, so large model support is, so as Maxime mentioned earlier, is part of of WLM-CE, but no longer of OpenCE. So it means that it's not supported. But the code for TensorFlow and PyTorch is still available, but it's not supported. And for example, for PyTorch, it's available for the 1.5 version of PyTorch maximum. So if you are, so bear in mind that if you want to use large model support, it's no longer supported yet. So nobody has reactivated this project. And if your project or your training script has to evolve later on in the future to a newer version of PyTorch or any components, that you could be limited if you are using large model support. So how it works in a nutshell. So without large model support, you have the GPU memory in red, where all the input data from a batch size that you are going to train, and the tensors that are produced by the different layers of my model, as well as the parameters of my model, as well as the kernel. So the code of the kernel has to be kept into this limited GPU memory. If at one point in time the kernel are not accessing data that are not located into the GPU memory, the kernel will just crash and the training will stop. So typically, so if you have you are going to process your training for just one pass. Here, so I'm going to try to do the graph traversal of my model. So the forward pass and then the backward, the backprop pass. The first layer will produce a first tensors. The first tensor that has to be kept into the memory, as it will be used for the gradient descent during the backprop. And the next tensor will produce another, the next layer will produce another tensor, but you will see then that there is not enough space for the next, the third tensor in the GPU memory, and the training will crash, right? So if you activate large model support on the AC922, and just for mention here, I've put there the architecture of the AC922 so you can understand better the different components. So we mentioned already that the memory bandwidth between the memory and the CPU is actually around 170 gigabytes per second. The NVLink from from the P9 to the V100 is 150. And then you have also to consider the bandwidth from the graphical, so the GPU memory based on the HBM2, 32 gigabyte, to the actual V100 chip itself. So it's around 1 terabyte per second. So it's good to bear that in mind to give an order of magnitude. So if we are going to swap tensors from the HBM memory to the DDR4 system RAM, you can see that for sure we will pay some time to do the traversal of the different buses, and they are not at the same speed. But let's move on to how it works. So now you have you can train the first layer. So for the first layer we produce 1 tensor. We will swap it into the system memory, and so on and so on. For the last tensor, we can keep it into the main memory, as it will be used immediately for to compute the gradient and apply the weight changes, update on the layer, and then same for the tensor 2, and then we recall tensor 1. That's how it works. So it allows to handle a higher resolution. So you can see typically some numbers here. For GoogleNet, it's 10x. For 3D unit, it's about 5 to 8x. So usually it's this order of magnitude. So you can really handle larger image resolution. So I've put there some use cases. I'm going to go through that very rapidly because we are running out of time. For 3D, so it's a 3D unit cases against for the PraTS project, which is the brain tumor detection. For brain tumor detection, so it's we have a specific 3D unit that detects the tumor inside the 3D CT scan, MRI scan, sorry. And what is important to consider is the performances you can get when you actually train such a model with a higher resolution. It improves a lot the performances, so the accuracy, so the dice coefficient in this case of your model. So having more resolution will definitely improve the performance of your model for sure. Then it's a question of performances in terms of throughput. If we've seen with the architecture, the description of the IC922, that you are going to swap the tensor from the HBM memory to the DDR4 main memory of this IC922. So what is the overall? So in this graph, we show on the x-axis the different resolution of the CT scans, of the MRI scans, sorry. So you have to cube that in order to have the idea of the size of the whole image. And on the y-axis, you have the throughput, typically the number of millions of voxels that are proceed per second. So the first line in gray, dark gray, is without LMS when it fits in memory, and the light gray line is for with LMS, so it's using TensorFlow. And you can see the overhead is about 10% in terms of throughput. But then there is a point where it declines a lot more. It's because at one point in time, I mean, yeah, I have to say that large model support will try to prefetch tensors the most possible way. So the kernel, the next kernel, when it has to actually access the tensors, don't have to wait for the transfer. But it's only possible when you have enough space to keep one tensor into the GPU memory. And for very, very large tensors, it's not possible. So you have to wait for free spaces to be made into the GPU to actually transfer these very, very large tensors. So that's the case when we have very large images, so it will produce very large tensors, we have this effect. Another case for wide slide images again, so I'm going to go very rapidly. We see the same effect for the throughput. And NLP, so it's Maxime actually that did this test, so I want to really go fast because I want to show the code itself. So with NLP, we have also very good results. And also another example from Maxime with a PSPNET for ADAS, so Automotive Driving case, where actually we improved a lot the accuracy as well. And we used DDL, which is now replaced by overrode. So how could you use LMS in your own code? So it's very simple. For TensorFlow, there is one single, there is 2 lines actually to change. And actually a callback or a hook. If you are using the new TensorFlow structure, the new estimator structure from TensorFlow 2.0, you have to implement hooks with LMS. For PyTorch, it's even simpler. So you just have to import CUDA.setEnableLMS, and that's it. You can eventually play with 2 parameters from LMS, which is a limit size and the set size. So, but usually you can just run it with the first option, line option. That's very simple. So what we do usually here is just when we have to actually, whoops, what was it? Oh, it's there. Yeah. So what we do usually is if we receive a code, we just implement this line of code. So we just put an option here in the ArcPath to actually activate an LMS or not, and just if the ArcPath is set, actually enable LMS in PyTorch. So it's very simple. But there is some consideration to bear in mind. We have to ensure that active tensors are resident in the device memory during the computation. You have also to enhance GPU allocator to allow a victim of inactivated tensors. So all the tensors are so included weights and biases are eligible for swapping. There is no graph to analyze. So it was the case in previous version of LMS. So it's no longer the case. So it's more flexible. And the next thing is to consider is the next limit. So once you have LMS activated, it won't be magic. There is other limits. So you've seen, for example, 10x for ResNet 101. So it means that you are either the limit of the main memory, so the RAM capacity itself. Because you are going to swap all this huge data, and if you are using the 4 GPUs, it will put a lot of data into the main memory, and your world system can swap. And there is also a limit in cuDNN, as one single tensor is indexed based on an int 32. So it means that one single tensor can exceed the size of 2 GB elements time or multiplied by the size of the data type of the tensor. So if it's int 32 or FP16, FP32, and so on. So it's also hard limit that you can then hit with LMS. But it's I mean, you have increased your resolution a lot more before. All right, so you have access to some statistics as well. So here are the lines if you want to have a look to the behavior of PyTorch with LMS. And that's it for large model support.